Okay, first question. With pictures and words, describe each symmetry in D3, the set of symmetries of an equilateral triangle. So basically, the question is asking, what actions can we do to this triangle to end up with this same picture again? Here's an easy one. We can rotate the triangle by 120 degrees, and we'll end up with the same thing. Another thing we can do is rotate by 240 degrees. We can also flip the triangle across some vertical axis, and we can also flip the triangle across the two other diagonals. And here's one that people miss pretty often, is the do-nothing symmetry, as my professor calls it, where you just do nothing. So there you have it. Those are the 6 symmetries of an equilateral triangle. Okay, second question. Write out a complete Cayley table for D3, and is D3 abelian? So I'll just write out the table here. One thing to keep in mind is that when you're filling in each spot on the table, you want to follow the laws of function composition. So if we do R240 times V, then we want to do V followed by R240, and we'll get, I think, D. And if we do it the other way around, then we actually get D prime. So that also tells us that this group is not abelian. Okay, third question. In D4, find all elements X such that, well, that satisfy these properties. So here on the left, I have all of the elements in D4. So for this first part here, we want to find any element that when you do 3 times, you end up with a vertical flip. So that's just a vertical flip. And for the second part here, we can rule out any flips because you can't do a flip 3 times to end up with a rotation. That's impossible. So it's just R270. And for this third part here, well, that's just the identity. And for this fourth part here, now we're looking for any element that you do twice to end up with the identity. So we can just count in any flips, because if you do a flip twice, then you end up with, what you had from the beginning. And we can also count in R0 and R180, because if you do those twice, you'll also end up with the identity. And for this last part here, any element you do twice to end up with a horizontal flip, well, that's none of the elements. Okay, so fourth question. This is actually just like the first question, but with a pentagon. So I'm not going to go through all the work. As you can see, you can rotate 5 different ways, and you can flip 5 different ways. So here's my answer. You got 5 different rotations and 5 different flips. So this actually leads into the fifth question, which is for n greater than or equal to 3, describe the elements of Dn. How many elements does Dn have? And the hint is you will need to consider 2 cases, one where n is even and one where n is odd. So what I'm going to do first is just write out a couple of specific cases. So if we let n equal 3, then we just have D3, which is the ordinary R0, R120, R240. And instead of naming all of the flips, I'm just going to call them flips across diagonals, so D, and give them each a number. And so if we let n equal 4, then we have D4, which is 4 different rotations and 4 different flips. Now what I'm going to do is rewrite the rotations on the right, but I'm going to write them in a way where you'll be able to sort of see a pattern. So first we'll have R0, then we have R360 over 3, and then R2 times 360 over 3. And then for n equals 4, we have R0, 360 over 4, 2 times 360 over 4, and 3 times 360 over 4. So if we write this in a more general sense, then we have R0, R360 over n, R2 times 360 over n. and so on all the way up to r n minus 1 times 360 over n, and then we just have an n amount of flips. So if we add all of these up, then we'll find out that dn has a 2n amount of elements. And to address the hint, if n is odd, then the axes of reflection are from vertices to midpoints. And if n is even, then they're from midpoints to midpoints and vertices to vertices. Okay, so now we have a set of really similar questions, which I'm just going to answer all at once. So the first one is, explain geometrically why a reflection followed by reflection must be a rotation. So let's go back to my triangle animations, and let's consider the red, blue, and then green points to be sort of a positive sequence of points. And if we do some kind of reflection, it'll reverse that order, so we'll get, I think, green, blue, and red. And then if we reflect a different way, then we get our positive order back. We get red, blue, and green. Now explain geometrically why a rotation followed by a rotation must be a rotation. Well, that's easy. If we rotate a rotation, the order of the points doesn't change. We'll still have red, blue, and green. Now explain geometrically why a rotation and a reflection taken together in either order must be a reflection. Well, we know that a rotation will not change the order of the points, while a reflection will. So if we do a reflection at any point in our sequence of actions, then we'll end up with a reversed order, which we could have just gotten there with any kind of reflection. Now this nicely ties into the next question, which asks us to associate the number 1 with the rotation and the number -1 with the reflection, and describe the analogy between multiplying these two numbers and multiplying elements of dn. So just like in the previous exercises, if we multiply a reflection by reflection, we get a rotation, which is kind of like if we multiply -1 and -1, we get 1. And if we multiply 1 with 1, we also get 1, which is like rotating a rotation. And if we multiply just -1 and 1, or 1 and -1, then we get -1, which is like a reflection. Okay, so question 10. If R1, R2, and R3 represent rotations from Dn and F1, F2, and F3 represent reflections, then determine whether R1, R2, F1, R3, F2, F3, R3 is a rotation or a reflection. So what we can do is go back to the analogy from the previous question and substitute 1 for each rotation and -1 for each reflection, and we'll get that this whole thing is the same as -1, so this expression here is just a reflection. Okay, so problem 11. Suppose that A, B, and C are elements of a dihedral group. Is a squared b to the 4th, a c to the 5th, a cubed c a rotation or a reflection, and explain. So this time a, b, and c could be anything. They could be a rotation or a reflection. So we could go back to using that same analogy, and we can actually rule out a squared and b to the 4th, because regardless of whether a and b are negative or positive, they'll still be positive. So we'll just have a times c to the 5th, a cubed c. And if you think about it, since there's an even amount of a's and an even amount of c's, regardless of whether a or c are negative or positive 1, we'll still end up with a positive 1. So this expression must be a rotation. Okay, so problem 12. Which letters of the alphabet written in uppercase block style have a symmetry group with 4 elements, and describe the 4 symmetries? So let's take a look at the alphabet, and a lot of these letters actually have reflective symmetries or rotating symmetries, but the only ones that have rotating and reflective symmetries are H, I, O, and X, and their elements are R0, R180, V, and H for vertical and horizontal flips. Okay, problem 13. Find elements A, B, and C in D4 such that AB is equal to BC, but A is not equal to C. So I'm going to let A be a horizontal flip, and let B be a 90-degree rotation, and I'll let C be a vertical flip. And we'll see that AB is H times R90, which is D, which is R90 times V, which is BC. So there's that whole chain of equivalencies there, which gives us AB is equal to BC, which is what we're looking for. And obviously we stated that A is a horizontal flip and C is a vertical flip, which are not the same. So we are done.